Alright, so welcome to 7.01. We're going to continue looking at the mean and standard deviation as far as they are describing the center and variability of some data, and looking also at data that is symmetric and some that are not so symmetric. So let's go ahead and start out with a brief review of what mean and standard deviation really tell us. So this is the example that we took a look at today, where we have the study times for 10 students. And computing the mean is fairly simple, right? It's looking at the average value, so we sum them all and then divide by the number of data points, and we get 42. An average of 42 minutes is spent, okay? And so if we actually plot out our data, and we're going to use plots a lot to visualize our data, we can see that our mean lands right here in the middle of the data, okay? And that should make sense. Now, standard deviation is the average distance from each data point to the mean, okay? So the way that we're going to compute this is we're going to look at all the deviations from each data point to the mean and then try and compute an average. It's a little different than how we compute the average here, because if you think about it, 34 minus 42, that'll give me a negative distance, but I want to measure distance as a positive value, and so that's why I'm squaring. Okay? So to compute the standard deviation, I'm going to sum, basically take the deviation squared for each data point, divide by n minus 1, or 9 in this case, since there are 10 different samples, data points, I'm sorry. And then I'm going to take the square root, because I squared here, and so I want to take the square root so I can get back to a number that is not the square of the deviation. Okay? So I went through and actually did that. You can do this again, and what you'll find is that this is approximately 8.7. Okay? 8.7 minutes. So what does that mean? What does it mean to say that the standard deviation is 8.7 minutes? What this means is that on average, the data points are 8.7 minutes off of 42 minutes, which is the mean. So let's think about what that is saying. 8.7 minutes greater than the mean, well, that would be about 50.7. So here would be one standard deviation away from the mean. Now 8.7 less than 42, that's a little bit less than 34. And so I can see all the data points which are closer to the mean than one standard deviation, and all the data points which are further away. And I want us to think about why it would make sense that more points are closer to the mean than one standard deviation, and less points are further away. So why don't you pause the video now and think about why that might be the case. It all goes back to the standard deviation being the average distance that a data point is away from the mean. So the average, think about these data points in here. How much are they going to contribute to the average distance away? Well, these points are closer, so when I take the deviation between these points and the mean, I'm going to get smaller values. Whereas for these points out here, they're going to contribute a very big value to the standard deviation. So I need less of these big values to be further away and more of the smaller values to balance each other out, so that the average will be about 8.7. Okay, so hopefully that makes some sense as to why more of the data points should be within one standard deviation and less outside of one standard deviation, since we're computing the average. Okay, so now I'm going to go ahead and go back over some of the slides for how we actually compute the mean and standard deviation, and say a few things about them before we take a look at a couple of examples. So finding the mean of a sample, also known as x hat, and the way we want to think of the mean is just the average value of the sample, or what is the typical value that I'd find for that sample. And another way of thinking about this is what is the center of the data. Okay? We're always curious about what the center of the data is, and that's usually where we'll find the mean. So one way that people might ask about the mean is they'll say, well, what's the center of the data, right? What's the typical value that we'll find? Now let's look at standard deviation. Standard deviation is, on average, how far away are the data points from the mean? And another way of asking this is, well, how spread out is the data? And here's why that makes sense. Imagine you had a really big standard deviation. That would mean that on average your points are very far away from the mean. In other words, you would expect your data points to be spread out. If your standard deviation is very small, then you'd expect that the points are closer to the mean because the average distance away is very small. And so another way of thinking about standard deviation is to say, what is the spread of the data, right? Is it spread out or is it tightly bunched? If it's spread out, then I'm going to have a big standard deviation, and if I have a small standard deviation, then it's going to be closely bunched together. Okay? I'll go over just briefly how we find the standard deviation again. I'll first need the mean, because that's what I'm comparing each point to, and then I'm going to find the individual deviations, right? So for each data point x, the deviation is going to be x minus the mean. And what I'm going to do is I'm going to find that for every single data point. But I might get some negative values. So what I'll need to do is turn them all positive. And the way I'm going to do that is I'm going to square them. So I'm actually going to square each deviation and then add them all together. So it's going to be the sum over all of the data points from 1 to n. And then what I'm going to do is I'm going to take each data point, I'm going to subtract the mean, and I'm going to square it. And then I'm going to add that to whatever I have previously, and I'm going to do that for every single data point. And then I've got to divide, and I'm going to divide by n minus 1. Now remember I said it was a little different than the way we find the average. Instead of dividing by n, we divide by n minus 1. That's because we are dealing with a sample. Okay? We'll talk about later on, if I'm dealing with a true population, if I'm looking at the whole population instead of a sample, then I will divide by n. But for all samples, we're going to divide by n minus 1. And so that'll get us to this point, and what we've got to remember is that this is the squared deviation. And so to get back to the deviation that isn't squared, we will have to square root, and that will allow us to compute the sample standard deviation. All right, let's take a look at a couple of examples. Here we're taking a look at what's called a frequency histogram. And so this histogram below shows the distribution of battery life for 40 batteries that were sampled. They're all the same brand. And of course, you know, I'm sure you've used batteries before, not all batteries are created equal, right? Some last forever, some just die really short and you don't know why. It's probably pretty frustrating. And so when we do this sampling, we find that some of them are going to last longer than others. And so what we can do is we can create a frequency, a relative frequency distribution. And before we talk about shape, center, and spread, I wanted to make sure that we understand what the relative frequency chart is showing. So why don't we take a look at this bar here. And I want you to think about what this bar represents. So notice that it has a width of 5 hours, right? It goes between 95 and 100. So this bar represents all batteries that lasted between 95 and 100 hours. And the relative frequency tells me, if this goes, let's say that's 0.17, I'm sorry, yeah, 0.17, then that is saying that 17% of the data, right, the proportion of 0.17 represents 17%. 0.17 or 17% of the data is between 95 and 100. So 17% of the batteries lasted between 95 and 100 hours. Okay? So hopefully these should seem familiar, and it should make sense the more that we see them. Okay? One thing also to think about is that if I added up the relative frequency for all of the things I tested, what should it add up to? Well, it should add up to 100 or 1, right? So I should get 100%. If I look at all the data, it should end up being 100% of my data, right? So that's always something to make sure you check for. All right, so now we want to think about the shape, center, and spread of the data. Let's start with the shape. Okay, so go ahead and pause the video and describe the shape. You've probably will come up with a bunch of different terms, but there's one particular mathematical term that we're going to want to use. All right, so the shape. when I look at this data, it looks as though the left side of the data is similar to the right. So when the left and the right are the same, or very close to the same when looking at a data distribution, we call this symmetric. So this data is symmetric. Right, now let's look at the center. Now remember, we talked about what represents the center of the data. The center of the data can be best described by looking at the mean, right? That is really what the center of the data is. So go ahead and give a good approximation for what the mean should be. If I look at the center of the data, it's pretty, I wouldn't say obvious, but pretty clear that the center of the data lies at about 105. Okay? That seems to be a good approximation for the center of the data. So we'll say the center is about 105 hours. Okay, now we want to think about the spread of the data. The spread of the data is the sample standard deviation, right? The standard deviation here. How spread out is the data? On average, how far apart are the data points? Okay? And I'm going to give you three options here. 5, 10, or 25. And I want you to think about each possible standard deviation and decide which one makes the most sense. All right, let's first consider 5 here. So if the standard deviation is 5, that means that we're saying the average distance that each point is away from the mean is going to be only 5 hours. So let's consider what that would look like. Here is 5 hours to the right, and here is 5 hours to the left. Now, does this seem like an adequate representation of the average? No. Why not? Too much of the data is further away, right? Not enough of the data is in close, and so the average is definitely going to be further out to the right. Okay? Let's think about 10. So 10 hours to the right would be right here and right here. Okay? This seems to make a little more sense, right? Remember, the frequency tells you the percentage of data that's in this particular bar. So if this were 17 and 17, this is 15 and 17, that's pretty close to 70. So that's 70% of the data is within one standard deviation, which would leave, 15 and 15% on either side. And that should make sense because the numbers that are further away, those are going to contribute more to the average, right? They're going to be further away. Their deviations are bigger. And so we would expect less of them to be further away, right? So the average should have more data points closer in, but should still be pretty obvious that the average is at about this point. And if we look at 25, right, 25, this is one standard deviation to the right and one standard deviation to the left. And so here, there's very few that are further. Right, so this wouldn't make sense. The average should clearly be closer since almost all of the data is closer than one standard deviation away. So we'll go with 10. Okay? All right, so let's take a look at a couple more examples. All right, so here I have two relative frequency charts, and I want you to describe the shape and center for each of these. Okay? And you might need to come up with a couple new terms that you may or may not have heard before. So the shape and center for each. So let's think about the shape of this first histogram here. Notice that it's not symmetric, right? More of the data is on the left side, right? So this was what we will call skewed, okay? And it is skew in which direction? Right? More of the data is on the left side, so this will be skew left, and you can also say skewed, ED at the end. That works as well. Over here we have a situation where we are skew or skewed to the right. Okay. Now the center, because our data is skewed to the left and skewed to the right, the center of the data, right, the average, is going to be further to the left instead of right in the center, right? It wouldn't make sense for the average to be right here or right here because, right, more of the data is on the left. So if I had to think about where the center of the data, where the average is, I might think about something right? Where I'm trying to get sort of the middle of the data because there's more data points over here and more data points over here. Okay, so that would be where the center might land. All right, here are a couple more problems that I want you to take a look at. I want you to try these out on your own. If you want to copy down this histogram, you can. You don't have to. If it will help you out, go ahead. So let's go ahead and take a look at this one. This histogram is a result of a survey about the age of air conditioners for a sample of 200 residents. So the questions are, how would you describe the shape? Is the mean closer to 15, 20, or 25? And is the standard deviation closer to 3, 6, or 9? So go ahead and try this out on your own. You have all the tools to make it happen. And once you're done, go ahead and press play and we'll move on to the next one. All right, so here we have a curve, right? A distribution curve. And you've seen these before. You can think about this as very similar to a histogram. It's just that we've decided to use a smooth curve to represent the frequency of each value. So for example, frequency at 40, this would be where I'd look, and I'd look to see what the frequency is. And I want you to decide what is the best estimate for the standard deviation of this distribution. 5, 10, 30, 50, 60. And I want you to post in your comment whether you think it's A, B, C, D, or E, and a reason why. So you should probably have a question, right? Or maybe you're answering someone's question, and you should also post your answer to this question and why.